recording. So let's go through some of the FIR filter design. Wait a minute. Yeah, that's this one. Let's go through some FIR filter design things on MATLAB. And for that, let me open the what I'm asking here to do. Okay, first you need to compare the amplitude responses of different window shapes using window width of 37. Wait a minute, I probably need to, I will make a copy just in case that I don't destroy anything there. The original. So, different window shapes. So basically about the same thing what I have done on my material. Then how wide window you need in order to change transistor bandwidth by factor of 0.SS. So transistor bandwidth goes lower by that factor. You should be able to kind of guesstimate that one. You don't need MATLAB for that. Then design a low-pass filter with the following properties: sample rate, cutoff frequency given, stop and attenuation given, transistor bandwidth given, and other things given. So basically the filter composite, filter characterization is given by, well, that kind of box here. Sampling rate, the system property, cutoff frequency, that one, stop and attenuation here, transistor bandwidth, that one. Ripple given, minimum order, meaning as little calculations as possible. And yeah, and then use the previous model to design a band pass filter. Good. And then high pass filter. Design a high pass filter. Download a noises voice sample. Ooh, wow, that's nice, fun. Define the filter requirements to reduce the noise lower to than the voice. So you need to make a spectrum analysis, see where the noise is and where the voice is, and make the filter parameters based on that one. So requirements, what type, cutoff frequency, stop and attenuation, transistor bandwidth. Define those, and yeah, then you can basically do the same thing as the previous, either this first or fifth exercise. No, third or fifth part. Then designing the filter, verifying the filter, and using the filter. Okay, I'll show you something then. Pictures from my fishing trip. No, not like. Okay. I'll show you a little bit of how it could be done if we didn't have the toolbox. So first, try to get a say some values. So make a symmetric window, and let's see. How do we go through this? So let's there. We can go back to this FIR filter design thingy and windowing method. So basically, let's see that we are there. Yeah. Selecting -3 dB point of a low-pass filter, then selecting the window shape, and for stop and attenuation, adjust window width with transistor bandwidth. Yes, something like that. So first, I selected the region in interest. So I'm watching now, or looking after the system with a 31 coefficients, meaning 30th order filter. Next, sampling rate, for example, that 1000 Hertz would be just fine for sampling rate. So it's a measuring system. And then cut-off frequency, 100 Hertz or so, just for fun of it. Okay. And then basically what we can do is to calculate the, I will calculate the Nyquist rate, which is sampling rate divided by 2. And this is just to help the calculations. Then I can actually start making the window. So impulse response of the system. Fc divided by Fn is scaling factor, and then just sync Fc divided by Fn times Nn. So this is actually rectangular windowed sync. And basically the frequency response of this filter is simply something like that. C. Using the sync with those variables or those parameters. So basically sync at Fc divided by Fn times the Nn, meaning just the region of interest, which is symmetric by the center point, origo. And I can get a nicely behaving low-pass filter. Although, as you can see, the stopband attenuation is not that great. It's about 40 dB at most. So what we can do is to get some window shape, so a smoother window. Hamming and length of HH. And just for fun, I'll put there also the transpose, which is the prime operator. For historical reasons, these window generators actually are generating a row vector, but the coefficients are always like the other way around. Hey, the system coefficients are always marked as a row vector, but for historic reasons, this window generation actually is producing a column vector. Okay, so that's why we are transposing it. And that window, smoothing window, actually looks like this, a bell shape. And the frequency response of windowed sync, just multiply the window with the original impulse response, and now we have the Hamming window there, and we get something like, well, maybe I can actually stem plot. So we have the sync and the window on that one. Let's put that one there, and then we can actually do another figure and say frequency response of this windowed sync. There. Nice. So with this Hamming window, we got pretty cool attenuation, stop band attenuation. Let me take this one off. So That's the original with the rectangular window, and then we have this. This is the with this Hamming window, and this one has about 60 dB attenuation on stop, and this had about, well, actually to be exact, it has only about 22 dB, since the stop band is defined so that the attenuation is less than that 1 point. Of course, depends where you design the transition bandwidth. Okay, about the transition bandwidth then. For the rectangular window, our cutoff frequency was 100, and transition bandwidth is basically something like 17 hertz or so. So it's very fast transition to the stop band, while for our this Hamming window, the transition bandwidth is more or less like somewhere there. Where it is? Where it is? Maybe here. So it's about 54 hertz or so. So if you want to cut the transition bandwidth lower, you need to get more values. You mean you need wider window. Yeah, I know. It's funny to have wider window, but okay, well, believe me, we need a wider window. Yep. Okay, so wider window. So, for example, if we have this, if we want, well, 54 hertz was our original window with, sorry, 31 was the original window with, and we can scale these ones. For example, 54 hertz was the current transition bandwidth. If we want to drop this one down to 20, it means that we have to have 83 or 84 values on our window. Basically, window width. So it's just the ratio of the current window width divided by the desired window width, and you scale the current width with that one. So 83 or 84, well, 83 is just fine. This is not science. So n actually should be from minus 41 to 41. Always symmetric. Okay. There, nn equals from minus 41 to 41, and I overwrote the previous values, so I hope you don't get too confused of that one. I usually do. And then I recalculate this HH, also recalculate the window, recalculate the window sync, and then I can show that one there. Yes. So now I have a window sync with desired parameters like transition bandwidth is now something like 20 hertz, from 100 hertz to 120 hertz. So that's how you do the design for FIR filter. So basically you start from cutoff rate, you know the sampling rate, you have the ratio of cutoff rate divided by Nyquist frequency. that gives you a ratio to put inside of the sink. That basically controls the cutoff frequency. Then you pick a this window shape that it matches the stop band attenuation. And then on the last part, you adjust the width of the window so you can get the transition bandwidth as required. So it's quite straightforward way. The next point, without any tools, would be to have the modulation. The easiest modulation is the high pass, from low pass to high pass. You modulate that one with -1 to power of NN. So every other term. So this is actually the same as modulating with Nyquist frequency, which basically moves the zero frequency. Let's see, on this Z-plane, it moves the zero frequency to the pi. So this is low pass to high pass. There we go. Yeah. So we have exactly the same filter, but now it's basically around the Nyquist rate, just by simple modulation. There. Then from low pass to band pass, basically we go and modulate it with the FM flexible. Let's put this one at 240 hertz. This is the center frequency for the bandpass filter. Bandpass equals the original window sync times cosine 2 times pi times FM times NN divided by sample rate times 2. Okay. When you're modulating this one to or that one to be the opposite, it basically means that you're moving this one both that way and that way, or vice versa. You're just swapping the axis. But if you basically have some filter properties around the for example, low pass filter here, then you want to modulate it. Basically, it splits the spectrum in two, positive and negative. That's why you need to also scale it with 2. Rescale it back. Let's see. Bandpass filter. There. Now we have a bandpass filter which has the center frequency at 240 hertz, the modulation frequency. And then it basically on both sides it has this the amount. Well, the bandwidth of the bandpass filter is actually double of the original low pass filter. Okay, so that's the low pass, and then the third filter would be, or is it already fourth filter? Okay, yeah, it's a fourth filter. So band stop equals the low pass plus high pass. If these are linear filters, then basically Well, of course, you shouldn't do it this way. You first need to calculate separate filters. But anyways, if you add those, you basically have the low pass filter and the high pass filter, and the stop band is now a little bit uh, worse than on either of those. But of course, this is just arbitrary. Usually you have different filter on low pass and different than the modulated high pass filter. And then how about multi-band filter? Well, you just modify filters with different gains, and that's your multi-band filter. Okay, so that's the way you do it without any tools. But we have MATLAB. You can start Filter Designer. Click. Did you know? Oh yeah, I didn't know anything. Close. There we go. So that. Yeah, it was called Filter Designer. FDA tool. Let me move it a little bit like that. So where it actually starts, the design starts on setting up. Okay, I'll just move it like that. Filter design actually starts from selecting the design method, response type, and so on. And then you have this kind of box. We have the A pass actually there on the picture. It's the same as the ripple on band pass. Stop. A stop is the attenuation on stop band. Then you have F pass and F stop. So, and actually on this one you can, let's see, start, for example, playing with windows. On FIR window method, I have, which Hamming, I think I have. Hamming window, I can specify order, for example, 30 order. Use the MATLAB variables like fs for sample rate and fc for cutoff rate, and design the filter. Ta-da! So instead of typing those commands, you just use this graphic kind of filter design tool. Good. And then actually do the similar measurements from here and do all kind of sorts of analysis like phase response. Of course, this is linear phase filter. Okay, both on the same graph. Group delay. Well, it's constant group delay because this is FIR and R and symmetric. Impulse response. There you go, impulse response. Step response you can get. Oh wow, zero pole plot looks funny. This looks really funny because it has nearly singular values. And then the coefficients as a table. And then some information like, okay, discrete type, FIR filter, real type, so it's number of multipliers 31, number of adders 30, number of stages, states multiplications per input sample 31, additional per input sample 30. Okay, yeah, so you can actually start calculating what is the cost of the filter. Okay, how many multiplications that platform can do, or additions. Okay, now you can get into the performance parameters. And what else? Okay, tomorrow we go through a couple of those. But anyways, there's something else here, which helps you on on your filter design in real life, you can generate C header file, for example, as double precision floating point or some other types. Depending on your platform, does it have floating point unit or is it soft floating points? If it's soft floating points, then you don't want double precision float. You want the single precision float for that, since the software double precision floating point takes about 40 times more calculations than the single precision floating point calculations. And of course, the fastest way is to use the fixed signed integers with matching word length with the arithmetic logic unit of the processor, if it doesn't have the math coprocessor. I don't know about that one. That's something for you to find. But anyways, let's put the double precision floating point click and FDA coefs. There we go. Where's my what happened here? I hate when this happens. Let's see the editor. Okay, there we go. Home and yeah, the current folder. FDA coefficients. There we go. So this is standard C header file with the numbers already given there. And the MATLAB actually comes with their own data types. For example, this just has the definition for real 64T type, the double precision floating point number. Okay, and there's a table. Tabulated values, you can just include that one into your code and make your own convolution routine. Or take the DSP library for your STM32, which is a ARM processor. Let's see. So it's the ARM DSP library. From Kiel, CMC's DSP software library, which has filters, for example. Filtering functions. Nice. Convolution kind of filter. Yes, finite impulse response decimeter filters. Wow. Code tomorrow. Excellent. So you just need these set up the function and just use it in real life. It works just as easy as it looks like. So only what you need with the MATLAB is to design the filter and put the coefficients out, and then basically the implementation is already almost there, almost. Just just like IKEA furniture, some assembly required. Okay. So yeah, so you can actually play around with this filter design thingies, like what kind of different windows actually can give you Gaussian shape there, or Blackman window gives you that kind of this stop band transition. Oh wow, nothing changed here. But let's there. You can actually view the windows, what they look like, and what the frequency domain. That one actually already shows you what is the stop band attenuation of this window shape without doing any further calculations. There. What else? What else? There's also that Kaiser window. Basically, with a Kaiser window, you can fiddle one parameter to adjust the window shape for different purposes. Okay, good. So that's how you design FIR filters. Let me take a quick look on the exercise here. There we go. Exercise. Comparing windows. Using the previous, okay. Some answers here you can find with either FDA design tools. There's actual requirement of writing commands. You can always also just copy paste the screen dump of the FDA tool. If you are using the FDA tool to do. But otherwise, this is quite straightforward stuff here. Previous modules of bandpass filter with. Okay. Yeah. So everything can be done with the FDA tool. For example, that bandpass filter. FS FC1 would be 100, 240, for example. Maybe Bartlett, Blackman there, design filter. Wow, 10th order, 30th order. Playing with some parameters, it will finally give you what you want. Okay. Yeah. So, and let me take a quick look again here, verify your design. It's a response. Okay, design a filter. Yes, actually, this is just fine. Okay, again, a couple of hints for this part 6. When you download that voice, basically, it sounds something like this. There's some artificial noise which prevents you from hearing what is the voice there. But they are in different bands. I made it this easy, so it's quite clear when you do the spectral analysis which part is the person speaking, and which part is the noise part. Noise has always, well, it's random, meaning that the spectra look like the ones you already analyzed yesterday. Do I find one? See, there's one. All right. Hey, Caroline is not here. Too bad. So the spectrum analysis of noise. There you actually have the spectrogram which shows where the signal is. You will see some features. You definitely can recognize, okay, that must be the signal, and the lower part actually shows, okay, this is how it is in average, and it also shows you the noise floor. In principle, if you want to uh, filter this one so that you reduce the noise level, you can only do it by putting a bandpass filter to cut some of that noise and some of that noise without touching the information channel. Okay, so, and this here shows how much basically you need to reduce the noise, the difference between those. So for that voice example, the noise level is much higher than the voice level. Otherwise, you would hear already what this one actually was. You could hear the talk, but since you are not hearing, it means that this noise actually overcomes that one. That's how your ear works. And well, then you just need to decide how much you need to attenuate at least that noise in order to probably hear what the voice was saying. Okay, good. So I will let you now to work on this exercise for a while, and basically today I will also show you this IIR filter design hints. Well, it's practically the same. We just click different buttons on the FDA on the filter designer. But anyways, so work on this fourth exercise first, and then maybe after the lunch break, I will show you the rest of the hints for the next exercise.